Hi, this is Shivani and this is my Lab 4 Oscillations lab report. The purpose of this lab report is to observe oscillation motion using tracker software and create a computational model of the oscillation motion using VPython, and then compare the model with observational data and then finally compare changes in energy. In the tracker, we first uploaded the video. Then the blue calibration stick is used to create a reference for measurement. In this case, the calibration stick measured the distance of the length of the spring, 0.7 meters. Next, an axis was created using the purple lines. This serves also as a reference of positive and negative movements. Finally, from frame to frame, each center of mass is recorded as the ball moves around. On the right, a graph is created. The given quantities when starting this experiment include the mass of the ball, which is 0.402 kilograms. The video tracking software indicates the starting x position of the ball is negative 0.109 meters, and the y position of the ball is negative 0.633 meters when the time is equal to 0. These given quantities are inserted in the code in the beginning. Next, the values that are needed to be calculated for the code are the period, spring constant, and the length of the relaxed spring. In order to find the period, t, the amount of seconds between each oscillation was measured and then divided by the total number of oscillations to find the average. Next, to solve for the spring constant, we use the t calculated in the last step and use this formula to find k. To calculate the length of the relaxed spring, we must remember that in this system, the force of gravity is equal to the force of the spring. Knowing this, we use the formula and then calculate out the relaxed length. The values calculated out in the past slides can be inserted into the code here as the spring constant and the relaxed length of the spring. More of the code that was changed includes the box 1, which shows the calculation of force gravity and force spring using Newton's second law. Box 2 updates the spring movements in the visual representation. Box 3 serves to represent the change in energy over time. Here's the visual representation of the computational data. This graph represents the change in energy over time, with blue being kinetic energy, red being gravitational potential energy, green being spring potential energy, and yellow being total energy. The red line represents the observational data, while the blue line represents the computational data. They're both pretty similar, but the reason for difference is because drag force is present, and over time it catches up with the observational data and causes it to lag behind, while the computational data represents a true closed system without any drag force as interference. Question number 1. The first question asks, the energy principle satisfied. The energy principle states that change in energy is equal to net work. There's no work done on the system. With that being said, the sum of the energies present in the system should equal to 0. The graph that we acquired shows exactly that, with the yellow line remaining at 0 throughout the process. The next question asks to estimate the period of oscillation from x and y, and then compare the two position data. The period in the x direction is longer than the period in the y direction. From this, you can conclude that there is more movement in the x-axis over time and less movement in the y-axis over time. This is observed due to the fact that in the x direction, to calculate the period is affected by gravity and length, while in the y direction, the period is affected by mass and spring constant.